Let us look at proposition number 27, 28, 29, 30 of works of Archimedes, specifically from on conoids and spheroids. The proposition says, in any spheroid whose center is C, if a plane meeting the axis cut off a segment not greater than half the spheroid and having A for its vertex and AD for its axis, and if A prime D be the axis of the remaining segment of the spheroid, then first segment is to the cone or segment of the cone with the same base and axis is equal to CA plus A prime D is to A prime D. And the second part of the proposition says, as a particular case, if the plane passes through the center so that the segment is half the spheroid, it is double of the cone or segment of a cone which has the same vertex and axis. So let's do some construction. So we have this axis. Let us say we have a plane which passes through the axis, and we are going to cut this spheroid at D so that we get this circle of intersection. Let A be the vertex of this segment and A prime be the vertex of this segment. So AD is the axis of this segment, A prime D is the axis of this segment. We have a line of intersection between these two planes, and that line of intersection intersects the circle of intersection. Let us say this is B and this is B prime. Let's draw a tangent at A and let's mark this as EF. Okay, let's now draw this line. Draw this line. Now let's again draw a tangent at A prime, and we name it as E prime and F prime. So now here we can draw a cylinder, we can draw a cone with the same base and the same axis. We have AC plus A prime D is to A prime D, which is equal to AC plus A prime C plus CD. A prime D is equal to A prime C plus CD. Now, AC and A prime C are both equal. So we can write it as 2 times A prime C plus CD is to A prime D. Now, to work out this in our diagram, what we'll do is we'll mark a point H so that A prime H is equal to A prime C. Okay. So, which means now 2 times A prime C. This is A prime C, this is A prime C. So 2 times A prime C plus CD will be HD is to A prime D. So this we have converted into this. Now let V be a cone such that V is to cone ABB prime. ABB prime. This cone is equal to HD is to A prime D, implying V is equal to the first segment ABB prime. So V is a cone whose volume with respect to cone ABB prime is in this ratio. Now, cylinder EB prime is to V is equal to A prime D is to HD by 3, because a cylinder is to a cone in the ratio 3 is to 1. Now, to prove this, we will assume that it is not equal to V. Segment ABB prime is not equal to V, which means either it is less than or greater than V. So we divide the axis of the cylinder into equal parts, N, M, L. So I've divided into 4 parts, and I draw lines parallel to BB prime. This construction is, we have done it quite a number of times in the previous propositions. And now I circumscribe and inscribe figures on the segment. Now let's take these two cases. We are going to prove that segment ABB prime is not less than V, and we are going to prove segment ABB prime is not greater than V. Since it is neither greater nor less than V, the conclusion would be that it is equal to V. Now let us take the case 1 first, where we assume that segment ABB prime is greater than V. So now we circumscribe and inscribe to the segment consisting of cylinders or first-off cylinders with axes along AD and all equal to one another, such that circumscribed figure minus the inscribed figure is less than segment minus V. So when we do that, what happens? Inscribed figure would be greater than V. Why? Because we know circumscribed figure is greater than the segment of this spheroid. So since circumscribed figure is greater than segment, to maintain the inequality, inscribed figure has to be also greater than V. So now the frusta of cylinder about ND is the greatest. So this frusta is the greatest, and the greatest circumscribed figure and rest of the frusta will be equal to it. Now think of the cylinder in that each frusta is equal to each other, and the frusta around ND is the greatest, and the rest of the frustas are equal to that. Similarly, the circumscribed figure along ND is also the greatest. Now let's take the straight line dA prime. So this is equal to A prime D. A prime D. Mark A on dA prime so that dA is equal to AD. Draw as many squares as the slices of the cylinder on dA and along it. So we have 4 slices of the cylinder. So we will draw 4 squares. 1, 2, 3, and 4. This part for the moment ignore it. We will come back to this later. A prime D is equal to the capital letter A prime D in the figure, and AD is equal to AD. So if we subtract these two, what do we get? We get A prime, which is equal to 2 times CD. Now we complete the rectangles on these squares. So let's complete these rectangles. Let S be the area of each rectangle. This each complete rectangle, let it be S. Now from the first rectangle, take away a gnomon with breadth equal to AN. Now to build this, first of all, from A prime, we take a length equal to AN, and there we draw this rectangle, and below that we form a square. This segment is AN and this is DN. So this is AN and DN. So we are ending up with a gnomon. Similarly, from the second rectangle, take away a gnomon with breadth equal to AM. So again here from this point to this point, it is equal to AM, which means this length is going to be DM. So here we draw a square. So this is DM and this is AM. And similarly for the next as well. So this part would be AL and this will be DL. So we are ending up with these gnomons. And the last rectangle, if we try to remove or mark a gnomon, it will not be there. Why? Because remember, we took this length as AN this length as AM, and this length as AL. So the next one will be AA. AA is 0. So here there will not be any gnomon taken away. Here we are taking this as X. So that means this will become 2X. This will become 3X. You can actually look at this. This is ND, and MD is 2 times ND, because the slices are of equal heights. Similarly, we repeat this exercise for the rest of the slices. Actually, the last rectangle will have no gnomon taken from it because AA is equal to 0. Now, let's look at the first gnomon. First gnomon is this part. This will be equal to the entire rectangle minus this rectangle. So the entire rectangle is A prime D times AD, from which we are subtracting ND times A prime D minus AN. Now, what we'll end up with is A prime D times AN plus ND times AN. Now, AN is common to both, so we can take it out. AN times A prime D plus ND, and A prime D plus ND is A prime N. So we end up with AN times A prime N. So if we repeat this exercise for the second gnomon, we end up with AM times A prime M, and so on. And finally, last gnomon, that is this one, is equal to AL times A prime N. After gnomons are taken away, the remainders are, so remainder is this rectangle and this rectangle after the gnomons have been taken away. After gnomons taken away, the remainders are, let's say, R1, R2 up to Rn, where n is a number of rectangles. And accordingly, Rn is equal to S, because there is no gnomon here. And are rectangles each of length A prime and exceeding by squares whose sides are respectively equal to ND, MD, and LD. And finally, AD. Here, of course, there is no more. So, R1 is equal to CX plus X square. So, here C is equal to 2 times CD. A prime is equal to 2 times CD. We are marking it as C. And X equal to DN. So, this would be CX, C times X plus X square. This is C, this is X. So this rectangle is CX plus X square. R2 is equal to C times 2X plus 2X the whole square. Similarly, this is 3X plus 3X the whole square. And so on. So now, first frusta in cylinder EB prime is to the inscribed figure. We know it is proportional to the squares on their radii. So this is BD square is to PN square is equal to AD times A prime D is to AN times A prime N. Again, from previous propositions, we are getting this. So which means S is to first gnomon. How? Because remember, the first gnomon is equal to AN times A prime N, and the entire rectangle is AD times A prime D, and that we have said let it be S. So S is to the first gnomon. Similarly, S is to second gnomon, that is second frusta cylinder EB prime is to inscribed figure, that is the second inscribed figure, is in the same ratio as S is to second gnomon, and so on. But remember, there is no gnomon corresponding to the last frusta in EB prime. There is no inscribed figure here. So, which means cylinder EB prime is to inscribed figure is equal to sum of all spaces S is to sum of all gnomons. So, sum of all spaces S is to the remainders R1 plus R2 plus up to Rn is less than C plus B is to C by 2 plus B by 3. This comes from proposition 2 of onconoids and spheroids, which means sum of all spaces S is to sum of gnomons is going to be greater than C plus B is to C by 2 plus 2B by 3. Sum of all spaces S is to sum of all gnomons is greater than A prime D is to HD by 3, because this ratio boils down to this based on proposition 2. Now, sum of all spaces S is nothing but cylinder EB prime, and sum of all gnomons is inscribed figure. So, the ratio of cylinder EB prime is to inscribed figure is greater than A prime D is to HD by 3. Now, in the previous slide, we saw that cylinder EB prime is to V is equal to A prime D is to HD by 3. We can say cylinder EB prime is to inscribed figure is greater than cylinder EB prime is to V. That means inscribed figure is less than V, because cylinder EB prime, the numerators are equal. That means to maintain the inequality, inscribed figure has to be less than V. Then only this will be greater. But we have reached a contradiction. Why? Because we started off with inscribed figure is greater than V, and here we are ending up with inscribed figure is less than V. So, since we have a contradiction, we can say segment ABB prime is not greater than V. So, that brings us to the second case. Now, we assume that segment ABB prime is less than the volume of V. So again, we inscribe and circumscribe figures such that circumscribed figure minus the inscribed figure is less than V minus segment ABB prime. In the previous case, we took it as segment ABB prime minus V, which means since inscribed figure is less than segment ABB prime, V has to be greater than circumscribed figure to maintain this inequality. So now, based on the same kind of construction, first frusta in EB prime is to first in circumscribed figure is equal to S is to S. Because here, if you notice, the first frusta and the circumscribed figure are the same. So S is to S. Second frusta in EB prime is to second in circumscribed figure is equal to S is to first gnomon, and so on. And last frusta in EB prime. Now, in this case, there is a circumscribed figure. So, last frusta in EB prime is to last in circumscribed figure is equal to S is to last gnomon. So, summing it all up, we have sum S plus all the gnomons is equal to N times S minus the remainders. So he is taking one single rectangle, overall rectangle S, to which he is adding all the gnomons. So that means he is taking N times S, here 4 times S, minus the remainders. So N times S is to R1 plus R2 plus dot 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 Rn minus 1 is going to be greater than C plus B is to C by 2 plus B by 3. Again, based on proposition 2. But if this is greater, then N times S is to S plus all the gnomons is going to be less than C plus B is to C by 2 plus 2B by 3. Again, based on proposition 2. So here, cylinder EB prime is to circumscribed figure is less than C plus B is to C by 2 plus 2B by 3. which means cylinder EB prime is to circumscribed figure is less than A prime D is to HD by 3. Because if we evaluate C plus B, it works out to A prime D, and C by 2 plus 2B by 3 works out to HD by 3. So, which means cylinder EB prime is to circumscribed figure is less than cylinder EB prime is to V. Because in the previous slide we saw cylinder EB prime is to V is equal to A prime D is to HD by 3. So this here again cylinder EB prime, numerators both are equal. So that means circumscribed figure has to be greater than V to satisfy this inequality. In which case we end up with a contradiction, because we started off by saying V is greater than circumscribed figure. But we are ending up with circumscribed figure is greater than V. So which means segment ABB prime is not less than V. Means segment ABB prime is equal to V, since segment ABB prime is neither less than V and nor greater than V. So we have proved what the proposition is talking of. Now let's look at the second part, where the segment is half of the spheroid, that is cut off through the center. So instead of the segment being through D, it is going to be a segment passing through C. So immediately you notice that CD disappears since C and D coincide, which means C by 2 disappears, because C is what? 2 times CD. 2 times CD by 2 is CD, and CD disappears. So which means CD by 2 disappears. Now here CB disappears because C is 0, CB is 0. So what we are left with is B square. Hormones are differences between B square and X square, B square and 2X the whole square, and so on. So if we follow the same logic, we arrive at cylinder EB prime is to circumscribed figure is equal to B square is to 2B the whole square by 3. B square cancel out, and cross multiply, we end up with 3:2 ratio. Cylinder EB prime is to cone ABB prime is equal to 3:1, cylinder to cone. So which means cylinder EB prime is to circumscribed figure is to cone ABB prime. If we take it X equally, we end up with segment ABB prime is to cone ABB prime is equal to 2:1, which is what this part of the proposition is talking about. So that was proposition 27, 28, 29, 30 of works of Archimedes, specifically from on conoids and spheroids. Again, let me remind you, there is a link to a PDF book which describes all these in detail. Please feel free to download it, refer to it, and if you think somebody else can also benefit from it, please do share. That's it for now.